There we go. So we're going to talk more about aromatics today. So I'll go through and kind of show you guys another way to test if something is aromatic or not. And so we're going to learn what's called a froth diagram. And these are designed for things between 4 and 10 carbons or so. And they're going to be able to help us predict if something is going to be aromatic or not. And how these diagrams work is, first you've got to draw a circle, the hardest part of this. And let's say we're looking at a 4-membered ring. Let's look at cyclobutadiene. So first step is draw a circle. Then you're going to inscribe the polygon representing the molecule. And one kind of important bit here is that one point must be at the bottom. And so if we look at, how that's going to work, so one point has to be at the bottom of our circle. So if we are going to draw our cyclobutadiene in there, it's going to be a square, right? That's pretty actually good for me. Terrible at drawing. So that's kind of step 2. So you have to put one of your points at the bottom, and the rest of them will go wherever they need to go to make your polygon work. And then each kind of point represents a molecular orbital. And then we kind of will draw a line halfway up, and we're going to see what that looks like. So if we draw our line halfway up, so it's going to cut through those 2 points, we're going to see that this is the anti-bonding up here, and these are the bonding orbitals down here. So if we're to draw the froth diagram for this one, we're going to have orbitals like so. This system has 4 electrons, right? Cyclobutadiene has 4 electrons. And so, if we're to put those in, always fill your lowest ones first, and we always fill degenerate orbitals equally before start pairing them off, right? So degenerate ones are the same energy, so had I drawn my square perfectly, it would be very clear that it's the same energy. And so, in order for something to be aromatic, all electrons are paired below the halfway line. Otherwise, we're going to be anti-aromatic. And so these diagrams, I mean, if the 4n plus 2 works for you and 4n works for you, that's great. If these diagrams work for you, that's great. We can look at another example. Let's say we have this dude. So this is a 7-member ring where we've got some double bonds and a lone pair. That lone pair can resonate in because there is space for it, and we can essentially move that around, so that lone pair does participate. So we have 8 pi electrons. So those pi electrons are, that number tells us it's going to be anti-aromatic, right? we already can tell that from the number, but we can go ahead and draw a froth diagram anyway. So first step, we draw a circle. And then we're going to draw our one point at the bottom. We're going to draw our cycloheptane. Are we going to get a number at the top? No, not really. Okay, hold up. 1, 2, 3, 4, 5, 6, 7. Nice. My drawings are getting worse and worse. Okay. If we draw our halfway line, we see that we have 3 orbitals below and 4 above. And so we have 8 pi electrons to put in here. So 1, 2, 3, 4, 5, 6, 7. Are these going to be? Yeah, these should be degenerate. I'm just terrible at drawing, but ideally those would be degenerate orbitals. And so we see here we have something in the anti side of this molecule, which means it's going to be anti-aromatic. So we have electrons in the kind of anti-bonding region. And so this is going to be anti-aromatic. Or we could have just counted 8 pi electrons. That's an easier way, in my opinion, to say right away that this thing is anti-aromatic. So you kind of have 2 choices. You can draw a froth diagram for something, or you can kind of make some deductions. So here's our rules. So option 1 is the froth diagram, and that will tell you if something's aromatic or not. Option 2 is to count the electrons, and then if we have 4n plus 2, then we have to then also consider, do we have a ring? So everything has to be cyclic, so there needs to be a ring there. And then the other question we have to answer is, do we have a planar ring? And then, what's our third question? Is everything going to be filled? Well, we already can deal with that with the other one. How did I phrase this? So we're essentially just looking, do we have that continuous ring where we have the overlapping orbitals in our planar thing? Oh, we have the electrons. Duh, that's the last thing. And then so if yes to all these, then we are aromatic. If no to any, we are anti-aromatic. And then, so that's the case that we're looking here. So if we do not have the right number of electrons, we're anti-aromatic. If we have something that's not working, we can also have non-aromatic systems. Non-aromatic ones are different. Those would just be like not cyclic, for example, like hexatriene. It has 6 pi electrons there, but it's not cyclic, so it's non-aromatic. It's not anti-aromatic, because anti-aromatic is a destabilizing thing. Aromatic is a stabilizing thing. Non-aromatic is just doing whatever. It's not affected by it. So something that's non-cyclic that could still have 6 pi electrons, that would be non-aromatic. If we've got 4 pi electrons, we're going to be anti-aromatic. If we're 4n plus 2, also with a ring that's planar, then we're okay. Then we're aromatic. So that's kind of the distinction there. So think I want to clarify this a little bit more, actually. What I mean by planar ring, can I just drag you? There we go. That means we have a continuously overlapping pi orbitals, or p orbitals, sorry. That's what I mean by planar. So we've seen that benzene is completely planar, right? Because it has that complete, nice ring of p orbitals. We're going to see something like this. Is not going to be continuously overlapping. And it's not going to be planar then. We're going to have a kind of a kink in this molecule. We see that this bit here has no p orbitals. It's only got sp3 orbitals. And so it doesn't really mess with anything with p. So we wouldn't consider this one. And we wouldn't anyway because it only has 4 pi electrons. So there's a lot of kind of overlapping concepts here. So we would say this is not continuous overlap. But it's also 4 pi electrons, so it's still not going to be aromatic. It's going to be anti-aromatic. Alrighty. In that case, let's talk about some reactions. I say let's talk about reactions, although today we're only going to learn like 3. But next chapter we're going to be doing tons of these, where we actually do quite a bit here. So, we've seen our dear friend benzene. If we try to oxidize this, we get no reaction. And we could use something like chromic acid. If you put chromic acid on this, something that's a very, very strong oxidizing agent, we get no reaction. Interestingly, also, if we do the same thing with just an alkane, we also get no reaction. But if we put them together, we now get something that happens. So, interestingly enough, well, actually, we have H2SO4, so we can go ahead and protonate this. There we go. We will cleave at the benzylic position. So we will be able to oxidize an alkyl benzene by cleaving it oxidatively, and we will end up making a carboxylic acid there. So it doesn't matter how long your chain is or how branched it is. I mean, it can't be tertiary. No, it can't be quaternary. So you can't oxidize something like this, but you can oxidize it if it's tertiary. You can oxidize it if it's secondary, primary. So toluene will be able to be cleaved this way. So you're good to go there. So you can do this with all manner of oxidizing agents. You could use potassium permanganate in basic solution. This would also work. You'd get the same product out. So you just cleave your carboxylic acid. And then you'd probably need a acid wash at the end, right? So first step, second step. if you want to protonate it, right? Because if we're brewing it under basic conditions, we're going to need to reprotonate at the end. So you can cleave off at a benzylic position. So exciting, our very first reaction here. It doesn't matter what the rest of your molecule is. That's just going to get cleaved off, so we don't really have to worry about it. What happens to the other side, of course? We are going to get 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. You'd end up getting the carboxylic acid on your alkyl bit as well. Notice we had 6 carbons here, so that 1 stays on the benzene. The other 5 become this 2 carboxylic acid on the other side. So those can be dealt with later. So far, very exciting reaction, yes? Let's see, what else have we got here? We have one we've looked at before. Whatever, I'm just going to do isopropyl benzene.
What was that reaction called?
Oxidative cleavage, I guess.
Oh.
Some of these have names, some of them don't. So, like this next one, we're just going to call bromination or something. So, not a fun name for this one. We will have one fun named reaction though in this section. Do you remember our NBS? We talked about it with allylic things. It brominates them selectively. It'll brominate benzylic positions selectively as well. Remember NBS. That's NBS. You can either use UV or heat here. You'll end up preferentially brominating through a free radical mechanism. You'll get your benzylic position to be brominated. So the benzylic position is the 1 carbon away from the benzene. So if we want a fun name for this one, this is selective bromination. Selective benzylic bromination, we'll say. If you have allylic things, it will probably brominate those as well. So just be aware of that. So it does brominate allylic or benzylic positions. So, but it won't brominate any other, it's not going to put it on a random tertiary carbon somewhere. So it has to be a benzylic one. All right, and this is through a free radical mechanism, but we don't need to go over it. Let's see. So that's one. We can install a bromine. We can install a carboxylic acid onto some alkyl benzenes. So we've got 2 now. This brominated one, of course, we can do all sorts of fun stuff, because now that we've introduced a bromine, we now have a leaving group on our molecule, and that leaving group can be used for many things. We can say, okay, let's take our brominated 1. This is now an ideal candidate for an SN1 reaction or E1. Either one, good idea to work here, because we now have a tertiary benzylic carbocation that we formed in the mechanism. Here, I'll do two arrows. So let's do an SN1 by throwing some water at it. If we do that, remember, it'll form a carbocation, and we will now have installed a hydroxy group there. So SN1 works really well with this because we have a very stable carbocation. Remember, SN1 and E1 reactions go through a carbocation mechanism, so that position there where the bromine will leave is exceptionally stable. So we are good to do all sorts of SN1 and E1 reactions here. If we do E1, say we use if we go crazy with an E1 reaction, we'll end up with a double bond instead. Remember, the bromine will leave, and then our base will come in and pluck off the proton, thereby eliminating that and forming a new double bond. So these work really well. This is not new information. SN1E1 reactions are last semester, right? Heat this, by the way. That's going to definitely help. These are not new reactions, but it's just showing you, once you've brominated the benzylic position, you're good to go with all manner of things you learned last semester. And then if you really wanted to say, okay, now I've got this alcohol, I can do other alcohol things with it. Or I've got this alkene now, and I can do all sorts of fun things with that. So, useful synthetic step. If you have an alkyl benzene to brominate that benzylic position, because now you can do all sorts of fun things. Alright, we could also do SN2 reactions if we don't have a tertiary one. So let's say we've got this one instead. Actually, it's primary. We'll make it secondary. We can make it primary, whatever, who cares. Let's see. What shall we install on this? How about something with a thiol? This will just be a standard SN2 reaction. So we've now got a leaving group. We can substitute things there. I have too few carbons. Whatever, some sort of nucleophile. Any nucleophile will work here. Nuke. Whatever nucleophile you decide to put on, you can go ahead and substitute off your bromine. So, again, you can selectively brominate that position. And then we know, once you have a bromine there, as a leaving group, it can do all sorts of things. Like these SN1s, E1s, or SN2s, you can do E2 as well. So, have fun. Go crazy with it. If it's E2, though, you're going to need another carbon there. But we'll be okay. We don't need to really worry about that. What else do we want to go over? That is a thiol nucleophile. So it's like this. Sodium methoxide, but with sulfur instead. So it's just like, yeah. So it's just like this guy. It's just this one instead. So Me for methyl group. So I could put CH3 if that helps. So sodium methyl sulfide. But you're going to put a cyanide on there, put whatever fun groups you're looking at. Let's just put E2 because why not? This one, though, we do need the extra carbon because we do need some sort of hydrogen source for this thing. We can go E2. We can put in, what's the base of the day? How about... let's put in potassium T butoxide. Do that. You can eliminate through an E2 mechanism as well. So, oops. Lots of stuff you can do. All this stuff way back from chapter 7, 6 and 7, somewhere around there. Substitution, elimination reactions, so don't forget those. So, all sorts of fun reactions. Alrighty. So those first two Actually, really only one is new. The cleavage is new, maybe. The NBS thing is probably old, but forgotten. And all of these substitutions, eliminations are also old but forgotten. So, still don't forget these. Remember we did substitution elimination with, actually most did substitution with the epoxides. Don't forget those. So, it's just substitution like that. So, alright, what else do we want to do with our benzenes? Let's see, we can destroy it. You can go completely crazy if you just like heat the crap out of this with some platinum or some other. There are a bunch of metals that'll do this. You can, like rainy nickel would be another example. You can just completely destroy your benzene, go to cyclohexane. Why though? I don't know, but you could. You could do that. So throw 100 atmospheres of hydrogen at it. That'll be fun. Poor molecule. You're basically putting it in a bomb at that point. So, yeah, you can have fun there. What else can we do with these? The Birch reduction, yes. So, you can reduce it that way. Get rid of all the double bonds. You can also reduce it using sodium and methanol and ammonia, and you end up reducing just one of your double bonds. And this one, Adrene, has a fancy name. This one is called the Birch reduction. And we're going to take a look at the mechanism here. So, here we go. I'm going to draw it out. Actually, I don't need to. Yeah, I will. Okay, let's look at the mechanism for this. So we're going to want to show some stuff here. I'm actually going to do it the other way just so I'm consistent with the double bonds I've drawn. So, what's going to happen? So sodium's got one electron. We're using solid sodium, so not a sodium ion, not sodium methoxide or anything. It's just elemental sodium. So what's going to happen with this is that sodium, I will use my light blue for the arrows, is going to go ahead and attack our ring. That's going to cause the double bonds in our ring to go ahead and, oops, that one's going to have to go to here. We're going to end up getting a free radical on one side, and, oops, we're going to get a lone pair on the other side. So let's go ahead and see what this will look like. So if we continue this on, I'm going to start with my ring. So we have now 2 electrons on that position. So we have the sodium's electron as well as one of the electrons from that double bond there. And so we will end up forming a lone pair there. Those 2 electrons in the middle end up forming a double bond on that side of the molecule, on the right side. And then we have just 1 electron as a free radical on the bottom of this molecule. So that's that. So the top 2 arrows that I'm going to like put a little green bit in, that forms our lone pair. We have the next set, which I'm going to put a purple. Those form the new double bond. And then our last one will just sit as a free radical on the bottom carbon there, on the opposite side of your lone pair. Next, we have, so with this, by the way, you have to do this kind of stepwise. So you have to put your sodium in first and then worry about the methanol, but since we don't do this in the lab, we're okay. Apparently I'm doing this in blue, but we've got our methanol here. So our lone pair is going to go ahead and pluck off a proton. The methanol is just a proton source for us. So we're just using it to protonate our benzene. Oops, wrong color. So we do that. I'm going to go ahead and draw one of those hydrogens in black, the other one in, let's say green. Let's make our methanol green. So we have now a green hydrogen on our molecule from the methanol. We still have that free radical at the bottom. So what happens next? Another sodium, also just chilling there, is going to go ahead and just give its electron in, giving us a new lone pair at the bottom. I guess I've not drawn my hydrogen. We'll be consistent there. So now we have a lone pair there on that carbon at the bottom. And guess what's going to happen? Same thing as before. Another methanol is here. This time it's purple because why not? I like using fun colors. Gonna go ahead and protonate itself, which ends up getting us to our product. So we have a purple hydrogen and a green hydrogen, and then our original hydrogens on there. The ammonia is your solvent for this reaction. You do this typically at about -78 degrees. Very cold reaction because you don't want your sodium to be reacting with the methanol instead. So this reaction takes a benzene and reduces one double bond and kind of relocates another double bond to be on the opposite side of the double bond that remains. So you'll end up protonating opposite sides of your benzene. And what's important with this is that in some cases, say, depending on what you've got substituted on your benzene, you can choose where those double bonds will end up. So I'm going to just leave it on this mechanism for another, 30 seconds or whatever. I'm going to make it a little bigger. Or rather, change the orientation. So we're going to see that you can kind of make the parallel double bonds here, which can be useful synthetically. But we're going to see that depending on what we have, we can choose where those two double bonds are going to end up. In this molecule, it doesn't really matter because the benzene was completely symmetrical. There's no reason that we can't have made it parallel double bonds to somewhere else. It's just rotating the molecule anyway, so there's no difference. But we're going to see that if we put some sort of R group, say just an alkyl group, and we go ahead and do this, we're going to see that we exclusively will end up with this product. We do not end up getting the other one. We do not get this one. We don't get this one because I'm going to go ahead and switch our sides here. So hopefully the mechanism's okay. If you need more time on the mechanism, just let me know. But this position here does not get reduced because alkyl groups they are electron donating. So there's already going to be higher electron density there. So the electron from the sodium is not going to attack that position because it's already got high electron density. So because of that, the sodium is going to go to a side that has lower electron density. Let me write that out. So sodium's electron So the sodium's electron is going to go somewhere else instead of that position. So as a result, you're going to end up kind of going from, either here or here. Those would be the other positions that your sodium would attack. You could attack the other ones, but just resonate and you'll get the right structure. So you are going to still end up with your double bond connected to the R group still intact. That one stays there. So if you have an electron donating group on your benzene, you will keep the double bond on it, and you'll have the double bond parallel to whatever double bond you keep. So opposite side parallel. If you have an electron withdrawing group, on the other hand, if you do this Birch reduction, oh, shame on me to say that that's methanol. Same thing. I just apparently I'm inconsistent. And what else? Ammonia. If we do this, we will selectively get rid of the one that is on that position. So we will only get this position, or only get this product. We do not keep our double bond on the carbon that holds the substituent. So we don't get this one. Because now we have an electron withdrawing group, so we now have a place that the sodium is going to want to attack. So we will reduce that carbon. So just like the alkyl group being electron donating, preventing that site from being attacked, the electron withdrawing group welcomes the electron from sodium. And so we will always reduce that carbon if you have an electron withdrawing group there.
So,
yep.
Appears that anything alkyl related or anything that's connected to a carbon, it'll just be like the one at the top.
If it's only carbons, correct, yeah.
Okay.
You could also have a methoxy group. You could have an amine there. Anything that's got extra electron density. So because it's going to be important for us, I'm going to just quickly go over some electron withdrawing groups and donating groups. So that would be a good idea for us to review, perhaps. So alcohols, amines, ethers, these are all electron donating groups. So these will push electron density onto something nearby them because they can resonate towards it. Let's see what else is we have kind of, what's another good electron donating group? Good ethers there. We've got just alkyl groups. Carbons will donate electron density into things. So those can work as well. So we can even have esters in here. Those can donate electron density a little bit in as well. Those are kind of weaker though. I wouldn't even consider esters actually, because whatever, we'll keep them there. Some withdrawing groups: nitro, sulfonyl, carbonyl, formyl, the other side of the ester, and I'll put a prime on some of these so we have a distinction. Halides are also electron withdrawing. So with these, electron donating groups will force you to reduce away from themselves. So their carbon will stay as a double bond. Things that have electron withdrawing groups, you will always reduce that one, and you'll end up getting rid of the double bond on your electron withdrawing group. And always getting the opposite side there. All right, so hopefully a good thing to remember. So let's see here. Any other questions on aromatics? Alrighty, so that was the Birch reduction. So we're looking at, let's do one example. Let's do, let me find a good one here. I have one in my notes that we can do. Okay, here we go. Let's do an example of a Birch reduction, predicting where we're going to get those double bonds to go. And let's see. Oops. Wow, I really went far. Okay.
Could you give something that it would be similar to what you would give on a test or something?
Let's start with an easier one first. Well, honestly, it's really the same thing. Like, I can throw, look, here's some whatever random groups and stuff on. If you've seen the test I put in Discord, that's not representative of the molecules I typically do. That's Mrs. O's style. She likes big, crazy molecules that have 15 different things for you to worry about. I try not to do that because it's very hard for me to understand what's going on in your head if I have 15 things going on and you miss one of those things, and then that causes you to mess up, right? So I try to focus on kind of one skill at a time. So it will probably not get much more complicated than something like this. So don't be afraid by Mrs. O's stuff. She has a different kind of teaching philosophy in that regard. So she likes to really see that you're thinking of all the different things at once, and I try to not do that. So hopefully that'll allay some fears. We can do a slightly more complicated one. I'm okay with that. But really, we're looking at just a couple of things here. So, cool. Let's go ahead and take a look. So, if we're going to do this, we have essentially two places of substitution on our benzene, right? We've got the purple place and we've got the green place. Those are carbons on our benzene that have substitutions. Carbons that are attached to other things besides hydrogen. So we have to consider what is attached to those. So if we look at the purple one, we see next to it is this thing. That is a ketone. Carbonyls in general are electron withdrawing groups. So we've got an electron withdrawing group on the purple one. So far, so good. If we take a look at the other side we have just an alkyl group, which is an electron donating group. Thankfully, these work out nicely for us. So we always reduce the electron withdrawing group, carbon, and we never reduce the electron donating group, carbon. So if we go ahead and do that, if we do this reaction, we know we are going to therefore have our sodium attack this position here. If it attacks there, if we want to draw the mechanism, see, it's going to attack there, form our kind of lone pair there, and we're going to get our radical on the other side of the molecule. And then we have got multiple protonation steps. Suffice it to say, though, these green arrows here, that's going to show us where the new bond is going to be, the new double bond. It's going to be parallel to the one that we didn't reduce, right? And so, I mean, if we don't have to do the mechanism, I'll also save the time. We will end up having our reduction take place like so. All right. Any questions on that one? Hopefully we all see. You just get rid of the double bond that's next to your electron withdrawing group and move it, essentially. And we're going to get rid of the other double bond that resonates away, keeping the one on our alkyl group.
Question?
Yep.
Will we ever have two electron withdrawing groups? Or...
If you do, we can take a look at that. We want to kind of compare the strength of them, which is something that we'll learn later on more, but here, let's see. So here's two electron withdrawing groups. If we want to remember what's better, we might want to think about how these are going to work as electron withdrawing groups. So chlorine is just a single atom. It inductively will pull in electron density towards itself. But nitrogen, or the nitro group, oops, this is positive, this one's negative, has a place for us to resonate things to. So, for example, we can decide to arbitrarily resonate things towards that oxygen. I mean, I wouldn't do it in this case because there's really no point, but the nitro group is a much stronger electron withdrawing group. So that's going to dictate more than the other one. So same thing with electron donating groups. Your stronger donating group will control the reaction. So, but let's take a look here. So, nitro is a better electron withdrawing group. So therefore, we're going to say we have to reduce the blue carbon. And as a result, if we do our Birch reduction on this guy, because we have to reduce the one with a stronger group, then we will go ahead and say, let's say Birch. We're going to end up drawing that molecule badly. Okay, let me try one more time. There we go. Okay, so the NO2 stays, and we're going to end up having our double bond away from the nitro group after that. So that's what'll happen. And it'll be the opposite case if you have two electron donating groups. You'll choose the stronger one. They're roughly in this order. We'll formalize this order. I mean, as I've written the strongest ones up top. Amines are actually stronger than the oxygen. Here, I'll put that up there. So amines are your strongest electron donating group, and then hydroxy, and then ethers and all that fun stuff. So we're going to talk about what are strong, medium, weak electron donating groups and withdrawing groups. So we'll talk about that in the next chapter. So that's something that we will be talking about more. Okay, but suffice it to say, your stronger one will win. Alrighty. Let me see. Do I have any other ones I'd like to do for the Birch fun stuff? Okay, why don't we do some couple of synthesis problems? Let's do this. So, how might we make something like this? Well, probably a good place to start, as always, is to see what's the same and what's different. So our original carbon skeleton is 7 carbons. Ooh, wow, let me undo that. That was so ugly. Okay. This blue part is identical on both. So, we see here the only thing that we've added is an ethoxy group to this. Everything else is the same. We've added 1 oxygen and 2 carbons to this molecule. And so we might think, okay, well, what do we know? How can we add an ethoxy group? We can just brainstorm here. What's a way to add an ethoxy group to a molecule? Anyone at all?
Was it the oxidative cleavage?
If you do a cleavage, you're going to end up with a carboxylic acid. I mean, it's not to say that that's not something you can do. You could use oxidative cleavage as one of the things in a synthesis like this, but that's a harder way to do it, I think. Because you're going to then have to get rid of a carbonyl. So oxidative cleavage will give us a carboxylic acid. Right? That's what would be the product there. And so we have now added an oxygen, which is great, I suppose. But we have now this carbonyl business that we don't want there. But let's just look. How do we, we talked about ethers. How did we talk about them? What could we do to get an ether to be made?
Yeah, use Grignard.
Grignard could work. But since no, it won't really work. I mean, because you see here the new bond that we are forming is not a carbon-carbon bond. This new bond here is a carbon-oxygen bond. So Grignard is best for carbon-carbon. because otherwise, like if you try to make a Grignard out of this, it'll just react with itself, and you'll end up with diethyl ether instead. So probably not the best option there either. So our newest bond here is carbon-oxygen. How do we make a carbon-oxygen bond? We spent a chapter on ethers. Go ahead.
Say Williamson, but
Williamson works. That'll work. What do we need for Williamson?
We need an alkyl halide and an ethoxide.
Right. Alkyl. Let's try that again. Alkyl halide. We could even just say, yes, alkoxide works, but, yeah, we could say that. Or alcohol with base. Same thing. So, with this, we then want to think, okay, we could do this. So we have to think back to our original molecule. Is that easier to make it into an alkyl halide or into an alkoxide? Is it easier to throw in an halogen to in something with only carbons, or is it easier to put an oxygen on?
I think alkyl halide, if we...
I would
NBS
say
it, we
so.
could-
NBS it, for sure. So we know that, aha, that's right. If we say we've got our thing, NBS it, we now have an alkyl halide. Yes, you could totally make this a Grignard reagent and attack something with an oxygen, but it's a little... we have an easier way to do it. So that's our alkyl halide now. And so, if we want to put on that ethoxide, we just need the ethoxide. Plain old substitution reaction, right? SN2, that's what Williamson is. If you do that, you'll end up with your molecule. Oh, sorry, I forgot a lone pair there. So it's really just a matter of looking what's different about the molecule and what can we do to get there with it. And so we saw the only thing we've added to this molecule was an ethoxy group. Best way to put on an ethoxy group is have an ethoxide as a nucleophile. Sodium ethoxide is readily available. You can buy it. Super easy to make. We know how to activate benzenes, or rather the benzylic carbon, using NBS and bromosuccinimide to selectively brominate there, and then we can go ahead and do our substitution reaction. So, if nothing else, make your original molecule more reactive, do something to it. So, with the oxidative cleavage, we're probably not going to see it as much so far, except by itself, because we haven't learned reactions of carboxylic acids yet. So, in terms of synthesis, that's a little less useful for us. For now. Once we learn reactions of carboxylic acids, then we'll have more options open to us. Alright, let's do another one. So, in a synthesis problem, look at what's the same and what's different. So, what's the same is those. The only thing new we've added to this molecule is we've added one carbon and it's triple bonded to, wait, I'm missing a carbon. That doesn't make sense. We need to add 2 carbons. So sorry about that. There we go. Adding 1 carbon is particularly tough, but we won't worry about that. So we've added 2 carbons in a triple bond to our molecule. Molecule. So how might we go around doing this? How do we add this thing to a molecule? What was special about alkynes? They can do things that other carbons generally can't. How would we make this thing either a nucleophile or electrophile? One of them is, by the way, very much easier than the other. Between the two, nucleophile and electrophile. What's special about alkynes? Yeah, they have the triple bond. But we don't want to really react that triple bond because we still need it in our final molecule, right? So we don't want to get rid of it. Maybe if I draw this. What's special now with those things there?
Gonna say like cleavage, but
Cleavage will ruin our alkyne. So yeah. So if you try to do like ozonolysis or something, it's not gonna work. Yeah. Do you remember way back when, like chapter 2 or 3 or something, we talked about the acidity of those hydrogens? Remember that those hydrogens on an sp carbon, they're super acidic. Well, relatively. And if a hydrogen is relatively acidic, it can simply be removed and replaced with a lone pair. And so, if you were to take some a nice strong base, like sodium amide is, it's going to very happily pluck off your hydrogen, putting your lone pair onto the carbon. And that's relatively stable, right? Like, the pKa of this is about 25. Thereabouts. When you do your reaction, it's an acid-base reaction. You have our sodium here just counter-ioning. The pKa of the ammonia is about 35, so we're looking at a very kind of favorable reaction here. So this is very easy to do. And you end up now with, you've got a localized lone pair on carbon, which makes it a strong nucleophile. I don't know this. Okay, I ran out of space, it looks like. But it's a strong nucleophile. because now we have a lone pair on carbon that's ready to go ahead and react with something else. So, being a strong nucleophile, we may want to use this as the nucleophile, which means we need to turn our benzene into something that is an electrophile. Or we might think of it as give it a leaving group, something for it to be attacked that it can leave. And what's a nice leaving group that we might be able to put on our benzylic carbon there? It's Ramon's favorite. Here we go.
Oh, I would say OTS.
No. We don't need to tosylate because that's for alcohols. Just NBS. NBS, same as before.
NBS.
NBS, yep. So NBS turns our benzene into oh, I'm sorry. We started with toluene. So if we NBS it, NBS will turn that into having a bromine. A bromine means that this carbon now is electrophilic. Because the bromine is going to be withdrawing electron density a little bit towards itself, we're going to have a slightly positive carbon there. So, and a slightly negative bromine. So now we can say, aha, our little friend here can come in and kick out the bromine. Notice that this is only 2 carbons, so I haven't done anything crazy. It's just 2 carbons. That's 2 carbons. We're only adding 2 carbons. And so we'll end up with our molecule of choice, or desired molecule, rather. So we will end up brominating to activate it, make it electrophilic. Then we kick out the bromine by throwing in our nucleophile, which was the acetylide ion, sodium acetylide. Kick out the bromine, and there we have it. All right, let's look at another one. Don't forget all these things we have in our toolkits. So, what the heck am I doing here? Let's see what's the same and what's different. Always look at that first. Whenever we're doing a synthesis problem, we look at what's the same, what's different. We still have that kind of isopropyl bit on the benzene. All we've done is move. We have moved that thing 1 carbon over. We've moved our alcohol from that benzylic position to 1 carbon away. So, or we can say we've lost this and we've gained this. So we've lost our hydroxy and we've gained a new hydroxy. That's 1 carbon away from where the old one was. So it's always imperative that you look at what's the same and what's different within these. So, what do we think has happened here? In this case, it may be easier to be like, okay, well, what happened? How do we lose a hydroxy? what happens if we just lose a group like that? Or fine. Let's not worry about that. Let's focus on the other one. How do we put a hydroxy on a molecule? How do we make an alcohol? Hopefully many ways we've seen now to make alcohols. You had an entire chapter on this. A Grignard to like an aldehyde? I mean, that would technically work, yes. Okay, I'll write it down. We have Grignard. That seems to be y'all's answers for everything. Which is fine. Okay, so if you attack an aldehyde with a Grignard, yes, you can get an alcohol. Okay, how else do we make alcohols? Mercury?
Yeah, mercury.
Mica.
Or oxymercuration, rather. Demercuration, okay. We got 2 of them. There's like only 10 more.
I was gonna say, from epoxides, will we
Yeah,
make an
epoxides
epoxide and
works,
we
yeah.
open the ring?
That works. Okay, that works. What else? I mean, I'll put a couple more. They may or may not be useful, but let's see. What else do we have? We have, let's see. We can go ahead and substitute. Substitution reaction, throw in OH as a nucleophile, kick out something, kick out a leaving group. That's one. We have hydroboration, oxidation. We have cleavage of ethers. We have what else can we do with alcohols there? We can just reduce, just reduction of an aldehyde. We have a lot of options here. A couple of these are better than others. We can use a couple of these to get what we want here. So let's look at what we need for these. Is there going to be a way for us to install an aldehyde on the carbon that has the oxygen? So this carbon, we'll just say, is the one that's going to have the oxygen now. Do we have a way to... Can we add an aldehyde here? I don't think so. It's not very easy to just stick an aldehyde onto a random carbon like this. So I'm going to say that these ones are not going to work in this situation. These are ways to make alcohols, but not this time. Alright, what else do we have here? Cleavage of ethers probably is also not very applicable because we don't have any ethers. We would have to make some other ether. It's just really just there's no ether here, so not a good idea. So we have 4 left here. We've got oxymercuration, demercuration, epoxide opening, substitution, and hydroboration oxidation. So, with these, let's look at the position here. Oxymercuration gave us an alcohol on what type of process? Is it Markovnikov or anti-Markovnikov? Is Markovnikov, right. And is that alcohol on the more substituted carbon? Along that green bond there. It's not, right. So that's not the right one either. But notice though, we do have an anti-Markovnikov spot. So this might be a good idea. This one could work too. Substitution would be a little harder because you need something on a primary one, so I would say substitution is out. But either hydroboration oxidation or epoxide opening would work well here. And for both of those, wow, like, I think someone is like chainsawing something right outside my window. Okay. Can you guys hear that? Okay, well, anyways, in either case, we need an alkene. For both of these, we want to think, okay, how can we get an alkene here? So we probably will need this alkene if we want to throw that alcohol on there. Right? So we know we can go from our alkene to our alcohol, either through opening an epoxide or through hydroboration oxidation. And if we want, do we know a way to make an alkene here? Yeah, we can just do elimination, either SN2 or E2. Either E1 or E2. Either one would work. Throw some sulfuric acid on here, it's done. It's gone. It'll dehydrate. You'll form the alkene. You remember you can take a tertiary alcohol, heat it up, and get the alkene, dehydrate an alcohol. We could also just do E1 or E2, any of these. We have a lot of options. We'll get that alkene. And then we want to then consider our options. If we do an epoxide opening, what's going to happen there is if we make the epoxide, we're going to need something that is going to attack the more substituted side. Remember that we saw if you have an acid catalyzed opening, we can get it on the other side, but we're probably going to end up having some trouble with this one, because most nucleophiles to pop open will attack this one. And if we do that, we're going to end up keeping our alcohol where it used to be. So we would need to do something special. We would need to somehow protonate that oxygen, but then have a hydride attack it. That's pretty tough. But we can also just do an anti-Markovnikov alcohol on this in just one step. Do you remember the reagents for that? We've got borane or diborane. We have NaOH and NaBH4. If you do that, we will end up with our... Did I just mix those two up? No, I think that's the right order. Been a long time since I've done this, but the hydroboration oxidation will be our way to go for this, probably. That'll be the easiest So most nucleophiles attack here. So that means we're going to end up essentially going back to our original molecule. So the ethoxide one is a little bit tougher to work with there. So I would say we're best off using our hydroboration oxidation. And I'm just going to make sure I have the reagents right for that. Let's see. Oh, what do you know? It's hydrogen peroxide, not this. Oh, duh, that's the NHBH4 is for the, that's for the alkoxymercuration. Okay, NaOH, H2O2. Those are the reagents you need for this guy. Your solvent, probably THF, as always. So, that's what we're going to want to do for this one. So, those are kind of steps to synthesis. So, always think about these things. You're going to have to go back, remember all those synthesis chapters about alkenes, about alcohols, substitution, elimination, all those. So, fun. On Monday, I know we're done, but on Monday, we have exam day. So, it'll be on Canvas. I will upload the file. A PDF of the exam. You can print it out. You can, if you have a tablet, you can write on the exam itself on the PDF. If you don't have any of those things, you can get out a blank piece of paper and do all your stuff there. What's going to happen is you are going to be submitting a PDF on Canvas. So either if it's on your tablet, save it as a PDF with all your writing, or you can take a picture with your phone using something like Cam Scanner, some app that will allow you to take PDFs on your phone. Cam Scanner works really well. There's plenty of scanner apps, so find one you like. Of all the pages, you're going to take a picture of them, and then, or you can just submit a PDF directly from your tablet, or scan it. If you have a scanner, whatever way you're going to do it, you're going to upload it on Canvas. So upload on Canvas, and then double check that it is uploaded. Canvas will let you see your submission, so you want to make sure absolutely that you can see what you've written there, because I'm going to be very strict about the time. You're going to have 9 to 10:45. So you have 10 minutes on either end to print it out, to upload it and all that stuff. So you'll have a little bit extra time to make sure that you can have all that going. Okay, so it will be available at 9 a.m. for you to print or do whatever, and you must submit it by 10:45. All right, so this opens and closes. You do not need to meet on Discord, correct? So I will be around, so just ping me if you have a question. If I've written something wrong or whatever, which is always a possibility, just ping me. Just do this. Something like that. I mean, whatever it happens to be. Or just be like, hey, I'm not sure what I'm supposed to be doing here, or whatever. It should be pretty straightforward. Same format as you've done in 105. So you'll have mechanism questions, predict the products, predict the reactants, synthesis, nomenclature. All those fun things. So Chalmers should give you a practice exam. I put one in extra resources there for Mrs. O's. So that's the kind of style we're looking at there. Again, Mrs. O's are a little bit more complicated than mine will be, so yeah. All right, we're out of time. Yeah, go ahead, Ajani.
Can you give a few problems that are like your style too? Because tomorrow we'll probably be going over.
Yeah. Okay. I will try and come up with some for you guys. Okay, and I'll put them here or on Canvas. So.
Thank you.
Okay, sure thing. All right, see you guys later.